very much, everyone, for calling in. I'm Steve Croft. I direct the student research programs for Breakthrough Listen, and we've had a great summer with our interns, both here in Berkeley and at our international partner sites, Astron in the Netherlands, Oxford in the UK, the University of Galway in Ireland, and the Sardinia Radio Telescope in Italy. We have a packed schedule today with all the talks lined up, most of them delivered live, and then there's a few of them that are going to be recorded. We have 10 of our interns here in Berkeley who are going to present after we take a short break around an hour and 15 minutes from now, and we're going to kick off with the folks over in Europe at the beginning here. I guess without further ado, we're already ahead of time, but we'll see if it stays that way. And our first talk is going to be from Param Joshi, so please take it away. Okay. And I will give you a warning at 5 minutes. So.
Yeah. Am I audible?
Yeah.
Okay. Yeah. Let me share my screen. Is this visible?
Yeah.
Okay. Yes. So, hello everyone. I'm Param Joshi. I'm currently a master's student studying in India, and I'm an Astron Jive summer student in 2025. And this project was funded by Breakthrough Listen. So I would like to thank them for having me want to do this project. So the project was basically about studying the radio emissions of a young and active M-dwarf star. And my supervisors here were Sanne, David, and Joe. So let us begin with the project goals. It was basically to reduce and analyze the V-layer archival data for our source star, which is an M-dwarf star. And then we had to detect and identify radio bursts from the star and understand the possible emission mechanisms involved for the burst and its impact on SETI surveys for the future. So let us first understand some basics of stellar radio emissions and its types. It is mainly divided into two categories, which is incoherent or coherent emission. Incoherent emission is basically when the phases do not add up and we get the intensity which is a bit less than the coherent ones, and also the circular polarization fraction is comparatively less than the coherent emissions. And this incoherent is mostly stochastic in nature and more stable emissions. And the coherent is mostly when the phases add up, so we have a very high intensity in the burst, and they are mostly very highly circularly polarized, and they can also be periodic in nature. And then coherent are divided mainly into two categories, which is plasma and ECMI. ECMI is electron cyclotron maser emission, which is basically beamed emissions from the star because of the magnetic field interaction within the electrons. And their bursts are very highly circularly polarized, more than 90%. And the frequency is dependent on the magnetic field. Whereas in plasma emissions, the bursts are not beamed and they are comparatively less circularly polarized. And they're also dependent on the electron density, the frequency. So this was the overall basics of stellar radio emissions. So let's now begin with what observations I dealt with. It was basically the VLA archival data set from 2007, and it was observed by Craig and Linen. We had 3 observing nights of 12 hours each, and we observed at X band at 8.4 gigahertz, and bandwidth was only 100 megahertz with 2 channels because it was EVLA testing antennas in those times. So we had kind of a lot of antennas which were in testing modes as well at that time. And the data processing pipeline for us looked like we mainly used CASA for all the data reduction and imaging, and then some customized Python scripts for plotting the light curves and for detecting bursts. So the pipeline began with some manual and automated RFI flagging. Then we calibrated the data sets and applied them. And then we had to clean and image the data. Then we could detect the star out of it. And then we can use our light curve code. We can analyze the data sets and see what's inside the data. This is one of the image that we had after cleaning all of the data and using CASA. So this is basically the source star for us, which is V374 PEG, and it is a very high resolution image of the source. And this is basically all of my results that we analyzed all the data sets. We had 3 bursts out of it, and the above plots are the Stokes I and Stokes V bursts out of the data set. But you can see that there is no detection in Stokes V, which is the orange one, whereas the bursts are only detected in Stokes eye. So that's also the reason that we have contradiction with ECMI. But in the plots and below, we can see that the burst, which is this one and the burst, this one, both occur at the same rotation phase. So the bursts are also periodic in nature with the rotation of the star, which is a hint of ECMI, but no Stokes V detection, which is contradictory in nature. So we don't really understand what's going on in this M-Dwarf star. So our interpretation is that it is mainly ECMI, but the bursts that we detect are two independent but very highly circularly polarized, and they both originate from the dipolar magnetic field of the star, but they align very perfectly to give us low total circular polarization of the burst. And there's a study by Barnali Das, which was basically for massive stars, but it's that as we go higher in the frequency, both the left and right-handed circular polarized bursts kind of align with each other on phase, and because of that, at higher frequencies, we don't see the lot of fraction of circular polarization, whereas at lower frequencies, we can distinguish both the fractions as well. But we have 8 gigahertz data, so we definitely could be having this hypothesis, and that's what we kind of interpret that should be going on, because the bursts are definitely periodic in nature as well. And the impacts on SETI research is that definitely we can reduce false positives, because it's mostly always important to understand the star first and understand what's the emissions and radio emissions coming out of the star. And once we understand what's going on with the stars and the astrophysics behind it, then only we can have a good technosignature survey, because also that the technosignatures we search are mostly narrowband that we want, and because of the radio emissions from the star, as you can see in the plots, there is spectral broadening as well. So the signal will get broadened spectrally because of some radio emissions from the star coming. So because of that, it will have impact on our signals and some possible technosignature behind it. And there's also an impact on habitability around M-Dwarf stars, as they are very small in size. So they have a small habitability zone. So the planets are nearby to the star, and because of some radio emissions out of the star, there's always a lot of impact on the space weather and the atmosphere of the exoplanet. So it's always very important to study M-Dwarf stars, because those are the most common stars in our galaxy. So when we understand them, it's always going to help us to search for technosignatures in a better way in the future. So that's all about the future work, that we have a lot of more data to analyze, which will cover C-band as well as X-band. And there's also more recent data as well. And there's definitely possibility of proposals to study the star with maybe more broadband frequencies, so that we can test the hypothesis that we have. And obviously, SETI-related study for the star as well is possible. So yeah, this is just my summary slide. I would like to leave with the slide, and thank you. And I'm ready to have any questions if anyone has.
Thanks, Param. We have time for one quick question.
Yeah.
And if you're online and have a question, please just unmute yourself.
Were those a time series several slides back? And could you talk about the x-axis scaling? How what's the duration of these bursts?
Yeah, the duration of the burst was roughly around 20 to 40 minutes or something. On an average, it's around 20-30 minutes per burst. Yeah. Whereas the rotation period of the star is around 0.4 days. So yeah, it's very narrowly beamed in phase of the rotation.
Okay, we should move on to our next speaker, who is Hamish Reid. Please take it away.
Right, so I hope you can all hear me okay. So yeah, my name is Hamish. I'm a master's student from the University of Glasgow. For the past 8 weeks, I've been working on the Arthropod Eye project with my supervisors, Joe Callingham and Aditya Parthasarathy in the Netherlands. The main goal of this project is to create a new all-sky monitor to search for radio transients in the Northern Hemisphere. So these are things like your fast radio bursts, long period transients, and of course, technosignatures from alien civilizations. When you're building an all-sky monitor, the key things you want is a high FOV to capture as much of the sky as possible, and naturally you want it to stay on constantly. Sounds like a no-brainer, but unfortunately, lots of high sensitivity telescopes will trade off FOV for sensitivity, and operations can be expensive if they've got quite a high data rate. So I've been working with Astron for these past 8 weeks. These are their 2 main telescopes. I've been working with WSRT, the Westerbork telescope. In 2019, this underwent an upgrade where they fitted these antenna arrays to 12 of the dishes. These are just densely packed groups of 160 or so antennas placed at the focal point of each of the dishes. And with these, you can actually get multiple beams on the sky per telescope. So in this case, that's 40 beams. That greatly increases your field of view. Unfortunately, however, this also increased the operational costs, which eventually killed the Westerbork telescope in 2022. So we have these lovely new antenna arrays placed in the dish, but nothing to use them with. So the Arthropod Eye project that I've been working on is aiming to repurpose these, basically taking them down, placing them on the ground, and pointing them upwards to use them as all sky monitors. Because of the ability to create multiple beams, you can actually quite nicely localize any detections. So you can see here, this is just a simulation, but it shows how sources on various different points of the sky can get flagged. The main goal of this project is to reuse as much from the old system as possible. So you can see underneath the dish there's a little bunker. That's where most of the back end's kept. We're planning to reuse as much of that as we can because radio telescopes are expensive. But we're going to be getting a back end from Breakthrough Listen sometime this autumn to handle the data writing and data acquisition side of things. My role in the project has to get everything ready for that. So basically dig up all the old control scripts for the telescope, make sure they're still running with the software that they're on. Some of it's been updated, some of it hasn't. And additionally, to make sure that the hardware is all fine. We've not been using it for 3 years now, so we need to make sure what's still working and what needs to get replaced. This has all been quite in depth. So part of this has been to create an operations manual for when the engineers arrive to install the final part of the backend, because unfortunately I won't be working on this project forever. This has involved, again, quite a lot of digging into the old backend, but the end goal is to have a operations guide that anyone can use to just get this thing up and running and get the transient search going. I've got 2 more weeks of the project, but we've recently just achieved a band pass for the first time. So that's measurement across the entire bandwidth of the telescope. It needs calibration, so it's not exactly how we'd expect it at the moment, but it's great for the point in time that we're at. So the next step is to basically perform calibrations on this, make sure it's giving us the correct values that we're looking for. And further in the future, we're planning to rewrite some of the control scripts to better fit the transient search side of things. And once that's all done and we get the data writer installed, that should be a new all-sky monitor for detecting, fingers crossed, technosignatures in the northern sky. So I just want to thank my supervisors and the operations team, and if you have any questions, fire away.
Thanks, Hamish. Questions? Whose dog is that?
Yeah, that's Joe's, my supervisor, Joe Callingham. Great guy.
What is your supervisor?
He's quite busy.
Sure.
It's more, if any of you have met Charlie Ash, she's been more the person I've been working with for this. I think she's got a PhD with Breakthrough Listen in Ireland.
Yeah. Any other questions for Hamish? All right, thank you, Hamish. Let's move on. Next speaker is Huang Li.
Let me share my screen. Can you see my screen now?
Yes, although there's a couple of windows that are in the way.
Oh, wait a minute. Okay, is it now?
There's a big sort of grey block on the right and up at the top that are blocking some of your slide.
Wait.
I think maybe these are your Zoom controls, Long. I think we had that before. Like,
So how should I turn it off?
it has gotten smaller.
Okay. Can you see it now, or still being like covered?
It's better. There's still a bit of a block in the top right, but it's better than it was.
I think it's good enough.
Okay, I think you can see it now, the entire slide.
Okay, go ahead.
Yeah, so hi everyone, my name is Long. I am the first year master student from the Erasmus Mundus master program. And right now I'm working on the internship at Andersson right now. My project is about hunting for exotic radio signals in the V-LoLSS survey. And my supervisor is Henrik, Christina, Joe, and Aditya. So, sorry. Oh, it's not moving. So first, what is V-LoLSS? V-LoLSS is circular polarization part of the low-far LBA sky survey. The low-far LBA sky survey is a survey covering the northern sky above the declination of 24 degrees and will be observed between 42 and 66 megahertz. With the total of nearly 2,000 pointings and the average of 3 hours observation times per field. And we have the target resolution that we expected to get is 15 arc seconds and the sensitivity of 1 megajansky per beam, which means this will be the most sensitive and the highest resolution observation for this bands of frequency. The aims of my project is to improve the pipeline for the calibration of the V-LoLSS survey and also searching for technosignatures and astronomical sources. So why do we need to do the calibration for this stock V data? So as you can see here, this is the image from the stock V, the stock I on the top, and the stock V of the exact same field of the sky. And actually most of this, there's not too many sources in stock V. And the more important thing is that most of the source here is actually not real, and they are caused by leakage. So what exactly is leakage? So the flux in stock V will be including the real flux of the source, the error, and the leakage from stock I. The leakage is usually caused by the instruments or systematic errors. And as you can see here, the way we measure how much leakage we have in these fields is basically by measuring the flux in stock I and the flux in stock V image. And these are the flux of all the source in these two fields that you can see on the plot here. And they basically completely follows the bracket in the function above, you can see. And this means that most of the source here are actually caused by leakage and they are not real source. So the only way for us to reduce the leakage is by calibration. So To do calibration for the low-far LBA, we will use package named as, the pipeline is named as LOW. It's usually used for calibration all LBA data, but we will add the leakage calibration at the end of this pipeline, because at that point, every single order effects have been already calibrated, like Faraday rotation, ionospheric errors. And then we add this part in the red square here, where we do the leakage calibration. And also we will do dynamic spectrum models, where we'll also generate the dynamic spectrum of more than 200,000 sources, which is provided by the paper about like exoplanet, like interesting source nearby, and also some Gaia sources of stars smaller than, like closer than 100 parsec from our place. And right now we are testing on approximately 10 fields. 3 have finished, and we have a lot of dynamic spectrum still being looked into. So how good is our calibration pipeline? This is the results of one of the fields that you can see. The above is the stock V image before the calibration, and the below is after the calibration. The leakage can be seen in the plots right here, where it's reduced drastically from 1.6 to 0.2%. This means that we can increase the sound to noise ratio by 5 times. And you can see clearly on the image here, all of these fake sources are almost disappeared in our like stock V image after the calibration. So beside that, we also generated a lot of dynamic spectrum from these fields that we finished. And right now we have approximately 400 dynamic spectrum for all the targets in these fields. This is one of the samples, like dynamic spectrum from that exact like single source that you see here in the image, which is basically a pulsar. And the dynamic spectrum here like is the best we can generate of which have the time resolution of 8 seconds and the frequency resolution of 24 kilohertz. And the reason why we chose this for testing is because this is actually an eclipsing pulsar, which you can see where in the last hour of observation, the entire like pulsar disappeared like immediately, completely from our image. So this is the end of my talks, and this the summaries. We are also right now scaling up for the entire full loss survey. And thank you for listening, and I'm happy to receive any question.
Thanks, Long. Questions? Again, for folks online, feel free to unmute yourself if you have a question. What's the maximum or the best frequency resolution that you're going to be able to get out of these data?
The best right now is 24 kilohertz.
And is that the best going forward as well, or are you going to be able to achieve finer?
Yeah, the best right now for us, like even going forward, is still the best created directly by the low-far telescope.
Hello, everyone. I'm Gordon Lewitt.
Are folks online hearing the sound?
Yeah, I can hear it.
Great, thank you.
I'm a fourth-year student at the University of Michigan, and I've spent the last 6 weeks at Oxford University with Doctors Joe Bright and Alex Andersson looking for anomalous technosignatures in Parkes data. So the goal of our research is to find technosignature anomalies from data taken by the Parkes telescope, and we're basing this off of a pipeline published by Caleb Painter in 2025 that did this process on green bank data. So the goal of Painter's work was to find high narrowband drifting signatures based on kurtosis values. So when you're looking at an observation with a narrowband drifting signature, you expect it to have high kurtosis value or a peak that's more peaked than a normal distribution. And when you're looking at an off scan or away from your target, it will have a less than normal distribution or low kurtosis value. So you can filter out observations based on these cutoffs. So there are 2 main issues with this process. First, there's RFI, and there's a lot of data. So these 2 histograms here show the L and S bands, which are the 2 bands that the Parkes telescope operates in. And these red blocks are the RFI heavy areas that aren't even really worth looking at for observations. So a lot of our possible spots are cut off. And then there is just a lot of data. So not only are there a lot of observations, but to get narrow enough blocks to potentially find a drifting signal, we need to cut these observations up into very small frequency bands. So it can cause our code to take a very long time to run. At the worst, it was about 1,000 days, but we've implemented some parallel programming and better use of memory to narrow that down to closer to 30, which is still quite a bit, but it's more manageable. So this is what Painter's pipeline looks like. First, we split the data into those small, about 2.8 kilohertz wide chunks, and then we remove the RFI heavy bands. So that would be those red blocks in the histogram from the last slide. And then a step that the Painter pipeline currently does that we aren't because of runtime is filtering out data with hotspots. This basically just removes observations that don't have enough of a strong signal to potentially have a technosignature that we can detect, and we hope to implement that soon. And then we check the on and off kurtosis values for our scans. So we expect the on scans when we're looking at the target to have high kurtosis values. So we set a minimum cutoff. And then we expect the off scans when we're not looking at the target to have a low kurtosis value. So we set a maximum value for those. And anything that makes it past this point is deemed a level 1 observation. And then we check for drifting signals, broadband RFI, and blips. So this is because we don't want any RFI that covers a wide frequency range over a shorter time scale to get through. We don't want any high power but short time and frequency signals to get through, which is what blips would be. And we expect signals to be drifting. So anything that is narrowband but not drifting, we also filter out. And anything that makes it through these filters is deemed level 2 and is meant to be followed up by I. So here are some of our initial results. We just got this code working finally last week. This plot shows the on versus off kurtosis values. And the biggest thing to see here is that the vast majority, 99.998% of data is filtered out by the kurtosis test. And this is versus Painter's, which is about 99.95, which doesn't seem like a huge difference, but for Painter, they had about 11,000 anomalies to go through. We have about 1,000. This could be good because it's less to do by eye, but at the same time, it might be too restrictive. And we wonder that this might be because the two telescopes we're using, we use Parkes, Painter used GBT. They have different properties, and we're not taking those into account when implementing these kurtosis cutoffs at the moment. Because the cutoffs have to do with the signal to noise ratio of 10, which they found adequate to find certain signals. And we haven't found the cutoff values that would produce that same signal to noise ratio for the Parkes telescope yet. But here's an example of a failed kurtosis test, which is most likely because there was high kurtosis in the off scans. So this waterfall plot alternates between on and off scans. And as we can see, there is a narrowband signal, but it's through the on and off scans. So it's most likely RFI. And this probably got filtered out because the off scans will have a high kurtosis value or more peaked than normal distribution in the off scans because there are these very high power parts in the off scans. And here are some examples of RFI that have passed all of the stages. They've become level 2 scans. So they have narrowband drifting signatures, except they go through the on and off scans and thus are most likely RFI. So there are a lot of refinements we still need to make to this pipeline to make it work well for Parkes data, but it is filtering out a lot of observations that we would hope is filtering out. So we're having a great start. And that is all. Thank you very much for your time. Feel free to ask me any questions on Slack or sending me an email. Bye.
So again, Gordon's talk was pre-recorded. Feel free to follow up with him. And now I'm going to load up the next talk.
Hi everyone, I'm Ella. This summer I've been modelling the radio frequency environment on the far side of the moon. I'm about 6 weeks into my project, so I still have a few weeks left, but I'm really excited to share what I've done so far. So let me start with why this is important. The far side of the moon is a particularly radio quiet environment, and that's because it's naturally shielded from Earth-based RFI. That's why we want to put a radio telescope there. The Lunar Farside Technosignature and Transients Telescope, or LIFT-3, is a proposed radio telescope that would take advantage of the incredibly radio-quiet environment on the Moon's far side. That makes it perfect for not only searching for technosignatures, but also for a whole range of other radio astronomy. But the RF environment on the Moon is changing quickly. In the next 5 years, we're expecting there to be around 30 lunar orbiters. And once they're up there, the Moon will never be this radio quiet again. That's why LIFT-3 is planned to land and start operating by the end of the decade. To make this possible, the mission's budget is kept relatively low at $150 million. So although the lunar RF environment will be significantly quieter than on the Earth, it's not going to be silent. And that's where my project comes in. My project is all about understanding how these future orbiters could affect LIFT-3 and the overall lunar RF environment. To do this, I've written a simulation with the provisional name FEARLESS, which is short for Farside Environment Analysis of RF Lunar Orbiter Emissions Simulation. So the simulation takes 3 input files. The first is satellite data, including their orbital parameters, lifetimes, and launch dates. The second is their intended emission frequencies, and the third is general information about typical unintended emissions from satellites. So using this information, the simulation calculates each satellite's position over time and checks which ones are visible from LIFT-3. It then generates RF profiles for each satellite and calculates the received power by the telescope at different times. So what have I found so far? On the left here, you can see histograms showing the number of satellite passes through each pixel during a 50-day period. The top one is simulated for now, August 2025, and the bottom one is in 4 years' time, in 2029. This shows a really good visual representation of the increase in the number of lunar orbiters over time. The dark area visible in the 2029 figure is just because there are very few planned missions that have inclinations close to 90 degrees, so we don't see very many passes in that area. On the right, the figure shows the received power by LIFT-3 at a single moment in time, covering 1 to 260 megahertz. At these frequencies, we are seeing the unintended emissions from satellites, as well as the background from the CMB. To get these emission profiles, I compiled observational data from 3 different papers that studied the unintended emissions of Starlink satellites on Earth. I then extracted the maximum and minimum EIRP values for each frequency band. On the graphs, the blue and purple lines represent the cases where all the satellites emit at the maximum and minimum EIRP respectively. This is unrealistic, but it's helpful to have upper and lower bounds. The black line is where each satellite is randomly assigned a power value between the maximum and minimum following a Gaussian distribution. So this is my current and most realistic model. The purple shaded area corresponds to LIFT-3's effective sensitivity. So you can see that in 2025, this emission would not be detected by LIFT-3. However, as time goes on and more satellites come into the field of view, it would become detectable. So I still have about 2 weeks left of my project. So there's still a few things that I have left to do. So far the data on the unintended emissions only covers frequencies up to around 260 megahertz. And there's been little to no research done at longer wavelengths. So my next step is to take the data that I have and extrapolate it to predict what emissions might look like at longer wavelengths. I also plan to project the number of expected lunar missions over the next 10 to 15 years based on current trends in order to model how the radio environment could evolve over that time frame. Okay, so I think that's all I've got time for today. But if you want to discuss more or if you've got any questions, then please feel free to reach out to me. I've put my email address on the screen here. But yeah, I hope you found this interesting. Thank you so much for listening.
All right, so again, no questions for our recorded presenters, but our next presenter will be going live, and that's Oto Ulrich. So please take it away.
Hi everyone, can you hear me? See
Yep.
me? Great. Let me share the presentation. All good? Can see it?
Yep. Yes.
Sweet. Excellent. Okay, so hello everyone. My name is Oto Ulrich. I am an incoming fourth-year student at Trinity College Dublin here in Ireland. And my project was about finding technical signatures in simultaneous observations of two low-fire international stations under supervisors Aaron Gold and Owen Johnson and Vishal Gajjar. Okay, so first of all, it would be useful to quickly introduce LOFAR. LOFAR stands for Low Frequency Array, and it's a radio telescope array here in Europe with 52 stations all over Europe. And it's got like two means of observing, two types of antennas, the all low band antennas or the high band antennas. They operate at the frequencies you can see here below, and we are making use of the 2 days a week, approximately 2 days a week, that they are allowed to use in a kind of a local mode, not as a part of the huge of the whole cluster. The LBA is kind of hard to use as just like standalone. So we are concentrating on HBA and using the high band antennas, which like one tile out of like the 96 tiles that are in Berkeley, for example, are like these perpendicular bow tie antennas that you can see here. And so I did these observations as a part of LOFTS, which is a survey devised by Owen Johnson, a PhD researcher at TCD. LOFTS stands for Low Frequency Pulsar FRB and Technosignature Survey. The main idea of LOFTS is to do observations weekly, pointing at zenith for about 80 minutes. Zenith because that's where the LOFAR telescope is the most sensitive, and we point with both the Irish LOFAR in Burr and the Swedish LOFAR in Onsala, and we use coincidence rejection for shortlisting our candidates. So I have analyzed 39 observations that happened between September 25th and November 20th of 2024. As I mentioned, each observation lasted about 80 minutes, so this gave me 52 hours of observation time in total. And yeah, the LOFAR was pointed at zenith at that time, approximately at zenith, with like having kind of balance between, because zenith in Ireland is not the same as zenith in Sweden, so approximately. And in total, we probed more than 3 million stars in these observations. And here you can see the HR diagram of all of these stars. So first, the data from these observations was analyzed using TurboSeti, but before that could be done, we need to barycenter the filter banks, and that means to change the reference frame from a topocentric frame, which is just a normal one which it is recorded at, or which it is observing at, to a barycentric frame by eliminating the Doppler shift induced by the Earth's rotation and moving into the barycenter frame, the frame of the center of mass of the solar system. And this was done using code that was created by Vishal Gajjar. And then once we had barycenter data, we can run TurboSeti, which is now, as you might know, slowly being replaced by Bliss. We have tried using that as well, but we had problems with it, so we reverted back to TurboSeti for the sake of time. And so the output of TurboSeti is that file of hits, and I created a KD3 algorithm to compare all of these hits and search if I've got any hits that appear in both the Swedish and the Irish station. I started with a tolerance that was frequency ±4 Hz and drift rate ±0.2 Hz. This gave me two common hits, which I'll show you later. And then later I relaxed this condition to ±20 Hz and drift rate ±1 Hz per second, which gave more hits, which they will be later analyzed by my colleague Shimon using his ML algorithm. So here is one example of something that TurboSeti flagged as a common hit, but it is very evident that it's not very common when we look at it, when we plot it within ±125 Hz, and it's like the drift rate is very close to 0, and we can see that the beam or the signal profile is very different. And similarly, we can see here. So over these 52 hours of observations, I was not able to find like a These were the only two common hits, and they are obviously not they're earthbound. And then this data was analyzed also for periodic transmissions. And this was done using Blips, which stands for the BL investigation for periodic spectral signals. It uses the fast folding algorithm from Riptide to search for such periodic signals in the spectra. And the candidates from Blips are then shortlisted in a CSV file and compared in a similar fashion as before with TurboSeti. And when we plot, so I got again loads of candidates from this, and then I have to go through them on my own. And so when I went through them, you can see here, like on the bottom right, a candidate from Sweden where there's a peak in the periodogram, meaning that there's a clearly periodic signal in the Swedish LOFAR. And Blips also tried to find something here in Ireland, but when we look at the pulse profile, there's really nothing observed. So again, I have not found any periodic signal that was present at both the stations, but I thought this would be at least representative of something being observed in Sweden and not in Ireland. So for future work, we also plan to use Spandeck to search for broadband extraterrestrial signals, and also as a part of the LOFT survey, further analyze the data using Riptide for pulsars and TransIndex for FRBs, because so far we have just focused on like SETI signals. Also, there have been some corrupted data that we encountered along the way, and for the sake again of the shorter internship, we just stuck with like using the good data, but the corrupted data is still useful. So this is what I'll be dealing with later to play around with that. Okay. That's it. Thank you very much for your attention, and thanks to all my supervisors for the help and patience, and thank you to Breakthrough Listen for funding this project.
Thanks, Otto. Questions? I have a...
this is Mark speaking.
Sorry, go ahead.
I got a question. The duration of your observation, how long was that? And do you know whether the source would be still in the beam at that time? And you didn't use on-off, I think.
No, you don't need to. So that's the main advantage, I think, of LOFTs here, is that you don't need to use on-off, because we are comparing these signals between Sweden and Ireland, which are quite far apart. So we don't expect them to have a common RFI environments. So whereas with a single dish you would use on-off, here you don't need to use it, and we just shortlist candidates using are they both in the same? We record at the simultaneous. That's why I call it simultaneous. We record simultaneously in Ireland and in Sweden. And if there's a signal present at the same time, then we can investigate it, and it's a potential space-bound signal.
Thank you.
Just a comment in terms of the signal morphologies that you're finding from TurboSeti. Ben Jacobson-Bell, my student who's here in the room, has a recent paper where he's looking for morphological similarities between signals found using TurboSeti. We also have some other students, I think you'll hear later today, who are using ML methods to look for signals that look similar. So that might be something to consider applying in the future, either with or without TurboSeti, just to see sort of similarity between signals at the two sites.
Yes, that's what Shimon is also doing a lot, to compare like the similarities instead of so that's where I was saying, instead of like having two common hits with that, which I can go through just on my own, but if I want to relax the conditions a bit more, 43 hits and more, as you want an automated pipeline, it's best to employ an ML approach.
Okay, great. So that's a good intro, I guess, to our next talk, Shimon. So I'll hand
exactly. Thank you.
Thanks.
Yeah. Hello.
You go ahead.
Can y'all hear me okay?
Yep.
Oh, savage. 2 seconds. Cool. 1 sec. Okay, does that all look good, yeah?
Yep.
Cool. Oh, 2 seconds. I'll just move the slides. I'll just present again, 2 seconds. Boop. Okay, yeah, so hi folks, my name is Shimon, and following up from what Otto was saying, I am our second Breakthrough Listen intern who got the pleasure to work with our LOFAR team here in Ireland. I myself, I'm actually a graduate from the School of Computer Science here in Galway, so I guess a slightly different background than the majority of the folk here. And like, I won't lie, it was definitely noticeable. And like the first few weeks were very much astronomy for dummies, sort of condensed course for me. And yeah, it was getting tough to up to speed, but like, yeah, thanks to the knowledge and help from the other folks, it didn't take too long to actually get a solid grounding in this and, start working on the cool stuff. So yeah, so picking up from Otto, my project involved seeing if we can basically apply any form of machine learning techniques to this problem of, interferometry at heart, and hopefully create a machine learning model training pipeline that could then be used in the future for creating models that could be deployed to look through telescope data in the background, basically. Well, instead of having astronomers always looking through the stuff themselves for potential hits. So let me just move the slide. Yeah, so I guess initially what hit me was that just the scope of the problem was very huge. And there's like an infinite sort of number of ways of, of even models they can apply for this. Fortunately, the project brief itself already had a mention of using an autoencoder and a contrastive neural network. So that was already a good place to start. And from there, I could kind of build on further. So I guess what's first, we just look at our facts. So ideally, when we have our input from our two stations from Ireland and Sweden, it's going to be a slice from our filter bank of the same dimensions. And then we basically, based on this input, we want to look at our parameter space, which is basically the data we can work with. So if we have, our filter banks, we have time, frequency, and then our main focus is our signal intensity values. There is also, the option of tapping into our polarization values, so our Stokes QUVs or, polarizations. However, unfortunately, I was promptly informed that if I wanted to do this in a dual-side interferometry study for my model, we'd have to run constant polarization calibration on the two telescopes, which was kind of out of the scope of this project. So now kind of for the mapping part. So the intention of the model was to basically be able to input a smaller subset or almost a tile of our original filter banks, just because they're so huge, 20, 30 gigabytes and thing, we can't fit that into a model. So we just take a small slice and then we look at a tile or a slice from Sweden and we look at a slice from Ireland. We then try to simplify them or encode them. We could also look at that as compression. And basically, if we compress image further and further, and then we flatten that into a vector, can we basically see if we have a matching signal between two frames? Will that encode in a similar way? And basically, if we have this very high dimensional point, which is our vector, a high dimensional vector, if we compare them between the two stations, maybe if it contains the same signal, the distance will be relatively low between them, and any signal mismatches are going to be very, very far away, basically. And then you can run a threshold and basically you can run a threshold to determine if a pair of images contains the same signal or it doesn't. So I guess if we take in two time synchronized frames from our two stations and then have them mapped to a high dimensional vector. Sorry, I lost where I was. Yeah, so sorry, there was two initial approaches to do this, where basically we can either teach our machine learning model to understand just signal data at its core and just have a very general, well-rounded understanding of it and basically see if it's able to tell differences from those images apart. Or we can look for specific signal types. So for example, you have your narrowband signals. With narrowband signals, there is a few characteristics that you could try and define or derive in a mat form for the model to see. So you could look at, relatively high SNR values, slight drift rate, for example, scintillation, trying to feed that into a model and have it look for individual narrowbands, let's say in this whole, in all those frames, basically coming from our Sweden and Ireland stations. But there was the other option where basically we can use our autoencoder, our encoder parts to basically, if we take a full slice and we encode that into a very simple image, if we try and reconstruct that image into its original, what the slice looked like originally, if our model is able to reconstruct those correctly, we can assume that when it compresses it, it compresses only the most important features of it. So similarly, if you take a file or an image and you zip it up, you compress it, and then you ideally, if you want to use it further, you can decompress it again and have it in its full size. So the idea here was that images that contain the same signal are going to be compressed in a very similar manner if they contain the same signal. And if they don't, they wouldn't be. And that comes back to our high dimensional vector, where basically those distances will be very, very far apart. So yeah, so here's our model architecture finally. So that's just our encoder part of the model, which is just their first half. So yeah, you could, if you visualize this architecture, it basically looks like a funnel where initially you have a lot of inputs coming from the original image, and it kind of goes narrower and narrower until you arrive at this very, very simple representation of our image. Throughout all these steps, you have so-called encoder blocks, and encoder blocks itself contain basically a smaller subset of, you could almost say, neural networks. Here we have convolutional blocks, which are sort of like separated. They're not the usual neural network where it's all connected, but they're actually convolutional blocks where they're separated slightly. And this separation allows us to look at individual features, let's say, of a filter bank. So otherwise you get a very sort of averaged representation of the original filter bank, whereas now we can look at like the likes of lines, for example. We can have a different convolution block sort of take out all the noise from the background. So every sort of block can have specific niches. And here, step by step, we basically have it compressing the image further and further until we arrive at our bottleneck, which is just the simplest representation of our image. Yeah, and that brings us on to our second part of the presentation, where basically we decode that image and try to get the original. If the reconstruction is accurate, we can assume that the model understands our image as well. And then the second branch out is our contrastive head, where basically this is the second part of our training, where instead of having the model reconstruct our original filter bank images, we have it map it into that high dimensional space. And we give it the data in pairs, where basically one data frame simulates data from Ireland, the other data frame simulates data from Sweden. And if it contains the same signal, we teach the model to basically compress it both so they're in the same sort of high dimensional space. Otherwise, give them a wide separation. We basically just punish the model if it makes an incorrect compression.
Shimon, you're over time here. Could you wrap up?
Oh, yeah, sorry, of course. So here are just some of our results where basically we have our reconstruction. So you can see over here where we inject the signal into our data and how the model actually reconstructed that data. So yeah, this is just kind of very quickly just results. And then this is the actual latent space. So over here you can see in the yellow we have our two basically filter bank images that have matches. On the left side having a relatively low space. And then on the right side we have a second almost group, I guess, where we have our mismatches. And then if you look at our sort of around the distance of 0.6, we have almost a very clear separation between the two groups. So if you wanted to run inference and run on real data, this would be basically a very good measure to classify whether two images contain the same signal or not. Here's an example where we actually ran this inference. And on the left-hand side, we injected the same signal to two different data backgrounds or frames, where basically our model said that, sure, there's 98.7% confidence in the same signal. Otherwise, we have an example of more so a narrow band, where also it gives a very high confidence score. And then on the right-hand side, we only injected one of the images with a signal, despite the image here on the right actually having a background which looks very similar to the original signal. But the model very instantly thought that there's 0% confidence as the same signal. And then just very quickly for future work. So that would include probably a pipeline for actually running the model inference on our two different telescopes, which it would require basically run it separately on two telescopes and then comparing the results. We could then also investigate our hyperparameter tuning for different sort of types of filter banks, or vary the number of generations, the SNR values we look at, and further see how the model does. And then we could also improve our training pipeline by having better data to give it than just the simple narrow bands I gave it beforehand. And yeah, and this is the end of my presentation. Sorry for going over time. So yeah, this is not the first time you're seeing the photo today, but yeah, a massive thank you for Aaron, Owen, Evan, and especially Vishal and Oto for all the help and fun we had during our placement.
Thanks, Shimon. Unfortunately, there's no time for questions, but maybe we can reach out to you on Slack if folks have any questions.
Yeah, sorry again for going over time. Thank you.
No worries. Thanks. Okay, so now we're back to recorded talks from our interns from Italy.
we couldn't present live, but here is my video. So first, I'm Osdea, mathematics and artificial intelligence student at the University of Pavia in Italy. And this summer, I've been an intern in Sardinia with Giovanni Betz and Giorgia Granata. My mentors in Loco were Andrea Melis and Mauro Piglia, but I also had to go to Vishal Gajjar, Sanne Bloot, and Daniel Check, Brian Lucky, and Chenot Tremblay. My project consisted of generating a list of targets for SETI observations with Meerkat 5B, estimated the number of targets that could be observed in a given time frame, and finally compare the results with previous work. But first, why is Meerkat 5B even good for SETI? And band 5B is the band that will be installed in 2027 that will be higher in frequency than current frequency bands. In particular, it will go from 8.4 to 15.3 gigahertz. And having a higher frequency band comes with different benefits. One of them is having less radio frequency interference compared to lower frequency bands. And then having higher frequency, we also have higher angular resolution, and thus it's easier to associate a signal to a particular star in the field, since there are less of them. And finally, the exointerplanetary medium is more benign in terms of propagation effects at higher frequencies. With this, I mean that since most exoplanetary systems are stars that are M dwarfs with planets that are at much less than 1 astronomical unit around the star, in these cases, there is a lot of stellar wind, and in such a turbulent plasma environment, the signal gets spectrally broadened when going from the planet here to Earth. So we actually get a signal that is broadened, and this effect depends on the frequency of the signal. And since we see that if we simulate the signals, we see that SETI core has some troubles trying to detect detect the signal when it's more broadened. Then looking at higher frequencies, it's much easier to detect it because it's a narrowband signal and not broadened. So when it comes to target selection, I did slightly different work for the Gaia DR3 catalog and the Semi-Exotica catalog. For the Gaia DR3 catalog, I just filter stars by strict quality metrics. I simulated 3 years of commensal observations with Meerkat in band 5B, and I got an example of list of targets that could be observed, and finally computed the equivalent isotropic radiative power for the targets and compared it with previous work. Similarly with Semi-Exotica, the only difference that I only kept the galaxies and galaxy clusters, and I assumed that each galaxy, for each galaxy, we could observe 1 billion stars in the field of view of Meerkat. Then again, I simulated 3 years of observations, and I computed the ERP. As for results, I have that for Gaia DR3, we have results that are very similar to the ones obtained by Check with Meerkat in lower bands, and in some cases is even better. When it comes to the Semi-Exotica catalog, we have that even though the results are a little bit worse than the ones got by Jose et al., which uses a catalog, a list of only 97 galaxies. If we keep all of the targets in the Semi-Exotica catalog, we have the opportunity of looking at much more galaxies, even though they're farther away. And that's it for me. Thank you for the attention, and thank you for the internship. Bye.
Okay, we now have another recorded talk.
Hello, everybody. I'm Giovanni Bezze, and this is the final presentation of my project, which is searching narrowband signals using the Blips pipeline with the Sardinia Radio Telescope data. So I'm originally from the University of Padova, where I'm studying for my master's degree in astrophysics and cosmology. And for this summer, I stayed at the INAF in Cagliari, which is the National Institute of Astrophysics. Here's a list of my collaborators, both in Sardinia and elsewhere. This is how the Blips pipeline was implemented. First, the observations are stored in FIL files, which are converted to H5 files using the fill to H5 command. Then each H5 is processed with the Blips find hits command, which outputs that file with the parameters of the narrowband signals it found in it. And finally, the TurboSeti find event Python functions applies the on-off filters and produce the plots for visual inspection. The first issue I ran into was that Blips has some very heavy GPU memory limitation, and it would run out of memory for the maximum number of find channels above a drift rate range of about 3.5 Hertz per second. This is valid for a single file. For multiple files, it would occasionally run out of memory still. So in the end, I did my search with a drift rate range of 2 Hertz per second, which ensured that no file got skipped because of the memory limitation. Another problem that I encountered was that Blips output files have a space where a tab should be. And this is a TurboSeti example of output, which is the correct way to do it. This is addressed by adding a couple of lines of codes that after the Blips output just fix this character in the pipeline. So this is a summary of all the files that I analyzed. It's about 2,000 files among the Galactic Center and the test input catalog observations. And this is the list of the usual filters that are applied in the find event part. In the end, hundreds of events were still present after filter 3, but from visual inspection, they were not viable candidates because a signal was present also in the off frames, but was often very faint or a bit wide, so it wouldn't be picked up by Blips. So I then analyzed all the same data with TurboSeti in order to compare it to Blips. And the main difference between the two are these artifacts that are shown in this drift rate versus SNR plot. And they become stronger for high drift rate, even though they span the whole drift rate range. And they are clustered in periodic bands where the period is equal to the unit drift rate of the observations. And the type of signals that create these effects are either very, very wideband signals or noisy parts of the spectrum, or even narrowband signals where the drift rate is mistaken by Blips. And almost every time this happens on a non-scan, it will likely make it pass filter 2 because there is no corresponding hits likely in the subsequent off scans. Another interesting thing is that there is an asymmetry in the hits at very high SNR, both in TurboSeti and Blips. And these are actual hits. It's not an artifact. And they do not show any spectral dependence. They are scattered throughout the spectrum. And they're not present in the test input catalog targets, which could be due to either the directionality of the observation or the fact that they are done at two very different frequency ranges. Another finding was that the distribution of hits in the SNR frequency plane has some periodic features in the SNR frequency plane. And these are created by real hits as the black dots have near zero drift rate, and they have also very high SNR. The ringing is the colored ones in this plot, and they do not show any periodicity.
And this would seem to indicate that the frequency response of the instruments is not properly corrected. So in the end, the two most critical issues that needs to be solved for Blips to be used at the SRT are first the GPU memory issue that we spoke about, and then the ringing should also be eliminated. It has to be noted that a similar issue was also present in Green Bank, and it was solved by correctly applying a PFB correction. This concludes my presentation. Many details have been omitted, but you can find them on the report in my GitHub. And if you're seeing this video, then I couldn't manage to connect in person, but you can ask me questions either on Slack or at the email that you see here. And finally, thanks to everyone for the opportunity to work on this project and for the help. It was really a great summer internship, and I hope to work again with you in the future. Goodbye.
Okay, so we have one last presentation that's been pre-recorded before we take a short break.
Good morning, everyone. I'm Giorgia Granata. I'm a master's student in astrophysics at the University of Cagliari in Italy. And I'm here to talk about my project titled Searching Broadband and Wideband Signals Using SPANDAC and Blips Pipelines with the SRT. My mentors are Maura Pilia, Andrea Melis, Vishal Gajjar, and Karen Perez. Why search for this type of signals? Well, extraterrestrial transmitter might employ broadband and or wideband pulses, single repeating bursts with exotic dispersion sweeps to encode information or signal artificiality. Also, periodic pulse trains offer an energetically efficient means of interstellar transmission. And also, a rotating beacon at the galactic center will be highly advantageous for galaxy-wide communications. Well, we've got the database from the Sardina Radio Telescope observations. The Sardina Radio Telescope is situated in Italy, in particular in this island called Sardinia, but we have to go in the south of the island near Cagliari to see the Sardina Radio Telescope. The Sardina Radio Telescope is a single dish with a diameter of 64 meters. During this project, I used SPANDAC. SPANDAC is a Python-based pipeline, and it searches the single pulses in radio data. It has also Heimdall, and so we can use the GPU acceleration for automated analysis of large datasets. And during my project, I studied the dispersion measure and the slope of the signal in the flow to where the frequency is represented as a function of the time delay. In particular, I found some issues. And in fact, it is a challenge at higher frequency to distinguish RFI from signals of astrophysical interest. And in fact, the time delay associated with the dispersion measure becomes extremely small at these frequencies. In particular, for example, for a DM of 4,000, the time delay associated is of 600 microseconds. So I had to put my attention to not to put the downsampling and to do my researches at high dispersion measure. And I had also zoomed the width with the common plot cans point pi. I tested SPANDAC with the pulsar B0355 plus 54 in the C-band. Okay, and after I passed at the analysis at the highest frequency, in particular in the K-band, here we've got the same candidate. On the left, we've got the candidate found by SPANDAC, and on the right, there is the zoom with the common plot cans point pi. And after, we've got another candidate, and we can see in all the two candidates that these are only only examples, but we can see in all the possible candidates an issue in the third plot, because in the second plot we can see a slope of the frequency. In the second plot we can see the slope and the changing of the dispersion measure, but in the third we can see any slope, so we can say if it is a artificial signal or a astrophysical signal. After I used the Blips, Blips is breakthrough listen investigation for periodic spectral signals, and it used the fast folding algorithm. I've done a parallel data analysis. In fact, Blips has got the CPUs and MPA, and I tested Blips with the pulsar B0329 plus 45 in L band. And after it was carried out over a total frequency bandwidth of 187.5 per 2 megahertz on whole data of the 2025. These are some examples of possible candidates found with Blips, but I have to say that possible candidates were only found on the TIC files. In fact, 0 candidates were found on the Galactic Center files. We've got, for example, this is a interesting signal on the Hoang, and also here and also here. These are 3 different candidates. For the future prospects, we have to say that for Spannac developing a model for the SRT that can identify remote specific RFI-related frequencies. Also for Spannac, combine the files from BLC00 and BLC01 with the command splice2 into a single file to extend the frequency range and better visualize the frequency variation over time. For Blips, configure the system to automatically generate empty CSV files, enabling comparison between on and off states. And also for Blips, extend the analysis to data from previous years, particularly those from the Galactic Center.
Hello, so I'm Maxwell Mamesha. My project for this past, do we need the timer going? There we go. I shouldn't have said that. I could have done. So my project this past summer was designing a broadband Wilkinson divider for the Allen Telescope's Arrays radio frequency conversion box. And I worked with Alex Pollack. I'm a student from University of Illinois, Urbana-Champaign. We'll talk about what those words mean in a second. So the Allen Telescope Array, it's an interferometer of 42 dishes. They're 6 meters, and they have this signal path. Many people here are used to dealing with signals in their computer, but those signals need a way to get there. They don't just magically go from space into computer. There is a signal path that involves analog components digitizing this. And specifically, this signal path is kind of old. It has some limitations. Some of those limitations are in the RFCB. Previous interns worked on the PACs. There's new Antonio feeds, but to try to expand the bandwidth of this array, there can be upgrades to RFCB. And one component in the RFCBs, the radio frequency conversion box, that can possibly be upgraded is this power splitter. Alex, my mentor, suggested, let's try making a Wilkinson divider for this. It's a pretty strange and kind of novel idea, because Wilkinson dividers are generally not broadband components. I'm not going to go through explaining everything here, but the thing that you need to understand is the length of this trace on the divider is related to the wavelength of light that you're getting in, and away from that wavelength, your operation falls off pretty drastically. There's some technology that we can mitigate that with, for example, a coplanar waveguide instead of a microstrip, which this uses. Possible that with a coplanar waveguide, we'll have be able to just have cleaner signals, and it'll be good enough for our specifications. And there's also the concept of a step divider, which we'll talk about in a second. Another thing to understand is scattering parameters. I don't want to throw this at you, but it's so important. These tell you how electrical signals propagate through networks. You have reflection at input and output ports, you have isolation, and you have transmission. Generally, you want the transmission to be close to 0 as possible. It says -3, but really close to 0. And then everything else should be as low as possible. The first step to trying to design a new RFCB and a new divider is getting a box to put this divider on. And this was greatly figured out by a previous intern, Monica Schaefer. She worked on the packs and she figured out how to make a coplanar waveguide for this specific substrate and such with optimized parameters. I took that, I took some manufacturer sizes, I took the size measurements of the RFCB box, and we made it. And on the left, you can see that we have a coplanar waveguide just sitting in space. On the right, it's enclosed in aluminum enclosure, and the S parameters look great. It's, as you can expect, they look a little bit worse in the aluminum, but it still works. So we tried a first attempt at the divider. I bit off a little more than I could chew here on the left, and I got complete spaghetti as my result. And I learned from that experience to start small. And I thought I was starting small, but I learned what small really was, which is just start with the simplest thing you can. This divider here, which gave us some things which we like to see, but we're not getting that broadband operation, and we're not getting a good reflection at the output ports. Well, the technology that we can do to get some broadband operation out of this is having a stepped divider. By using a multiple stage divider with multiple isolation resistors, you can take advantage of this thing called a Chebyshev transformer, and achieve a more broadband response from your divider. There were, within all the literature that I reviewed, there were 2 divider designs which could possibly work here. The bottom one uses their own resistors, custom made with length, width, and impedance. That's kind of hard to replicate. And the top one has a pretty simple design that uses a solid strip line, a suspended strip line, I'm sorry. And suspended strip line also involves changing the shape of the box, but it might be possible if we do a coplanar waveguide to get good enough response for our things, for what we want. So we tried another attempt, and we can see that we got a broadband response out of it. That's great. Unfortunately, reflection at the output ports is still too high. Alex suggested, let's make them circles. This way we can put vias in between the traces. And well, it's a little bit nicer, I suppose. We're running into the same issues here. And really the divider on the left, when we bring it down to single stage, this graph looks very similar to our initial design with corners that is kind of ugly. We want some smooth traces. This S parameter plot here looks very similar to this one. So sort of in conclusion, what we have out of this internship is a very nice simulation of the coplanar waveguide and the RFCB, and a partially working simulation of the Wilkinson divider. I chased down for multiple weeks trying to minimize any source of error that I could think of, and this is sort of the best result that I got, which has a too high reflection on the output ports to be useful as a divider. After that, there's isolation and frequency range, which can be tweaked and optimized. I'm pretty confident that we can get those to work, but this output reflection has been a challenge. There's 2 possible directions to take this in the future. We can either try to continue making this divider, or we can try to make a resistive splitter, which does not suffer from from this narrow band operation related to the length of the wavelength, right? We could also just use commercial components, which work very well for this. This is just an example of one commercial component. It has VSWR, which can be equated to S parameters and decibels. That is very low for reflection. It's great. So thank you for listening to my presentation. Are there any questions?
Thanks. Questions?
Yeah.
Your plots you made with the S parameters, that was done in simulation?
Yes, ANSYS HFSS, high frequency structure simulator.
And you get some reflection of the output. How would you model like what was attached to the output? Is there just a perfect termination or something?
There's a wave port that is 50 ohms impedance matched and connected to top, bottom grounds and strip in the middle. I know that there's no problem with these ports because it works for the coplanar waveguide. For just the strip going through, it's the same design and the ports work. So that is one of many sources of error that I've sort of seen that very likely not the issue.
We have time for one more quick question. Again, if folks online have questions, feel free to unmute yourself. Okay.
What are the pros and cons of using the commercial component versus designing it in-house?
The commercial component costs money.
Okay.
And it would be maybe, I would say, $500 per polarization, and it varies a lot depending on how you want to do it. It can be $2,000, but I would say probably able to find a deal for $500 per polarization, 2 polarizations per antenna, 42 antennas. That's $42,000 plus tax or whatever. That's the ballpark. And also it takes up space. It might, I haven't looked deeply enough into this, but it might warrant making a new box and manufacturing 42 times 2 polarization more boxes with amplification inside of the RFCB, which would be another thousands of dollars. That said, it's not one of the most expensive things on that array. These antennas are expensive, but it's good to try to push science first, right?
All right, let's move on. Our next talk is from Benjamin.
Oh, sorry, I didn't stop sharing. Okay. I get this thing in here. Okay. So hello everyone. Let's see here. All right, great. Hello everyone. I'm Benjamin. I'm a rising junior at Amherst College, and I worked with Aya Keller and Carl Van Bibber this summer. I'm going to tell you how breakthrough listening is useful for searching not just for aliens, but also for dark matter. The animations work. Okay, great. So as most of you are probably aware, dark matter makes up most of the matter content in the universe, and it only interacts with ordinary matter through gravity. So while we're very sure it exists, we have no idea what it actually is made up of. But we can make a few educated guesses about dark matter to try to help us search for, this mystery particle. So the first thing is that our Milky Way is full of dark matter. It's distributed in this spherical dark matter halo. And second, dark matter we expect it to be stable, but like other standard model particles, it should experience decay or annihilation. A very true to life animation here. And the hope is that at least one of these particles in the final state will be a photon. And that's really good because that photon will have a particular frequency corresponding to whatever the mass of the dark matter particle is, and it'll show up as a spectral line. And believe it or not, we'll actually be able to distinguish that spectral line from any other source in the galaxy. And here's how. So we're orbiting around the sun, just orbiting around the Milky Way, but the dark matter halo is static. So we're actually moving through dark matter as we speak. So depending on where you look in the galaxy, your dark matter line is going to be either blue shifted or red shifted. And if you kind of have a lot of observations and subtract the red shifted observations from the blue shifted ones, you'll cancel all the features out except for the red shifted component, the blue shifted component of your dark matter line. Since we're isolating for the Doppler effect, let's call this a Doppler asymmetry. And you can do a very similar thing for intensity because the closer you look towards the galactic center, the more dark matter you see and the stronger your signal is. So do the exact same thing and you get an intensity asymmetry. So this is a strategy we can use to actually search for dark matter in our galactic halo. And all we need is a little radio telescope in West Virginia, a good sky coverage so we can have enough observations to construct these asymmetries with high signal to noise, good frequency coverage to check a lot of possible particle masses, and a buttload of funding. I wonder what program is doing a huge radio observing campaign. So yeah, thanks to Breakthrough Listen, the search has been going on for a couple of years now, and LS bands have been analyzed. And this summer we focused on the CNX bands, where I was in charge of obtaining and analyzing the X-band data. So before we build these asymmetries with our data, we first need to make sure we get rid of as much of the background as possible. And we do that through this rolling normalization scheme, which you see here. So we fit a polynomial plus a Gaussian to kind of represent a possible dark matter signal. And then we blank out that Gaussian and interpolate the background with another polynomial. And so you can see that there are two windows. There's this the size of the rolling window there, and then there's how much of the Gaussian we're blanking out. Those two values have huge impact on the signal or noise we get when we normalize the spectra. So I spent a lot of time figuring out what the best values for each of these two window sizes is. And you can see here for multiple injections in the X band,
that the window sizes actually make a huge difference in the signal to noise of our asymmetries. And it really depends based on what the background is at a particular frequency, what the sort of optimal values are. But overall, I kind of found general consistency when you pick an interior window of 1.4 times the width of your expected signal and an exterior window of 7 times the width of your expected signal. So using those values, you can measure the sensitivity of the search. So what you're looking at here is at every frequency, this is sort of the minimum signal size you would be able to detect with this method at like 3 sigma confidence. And this is just for a small region of X band. But you can see the top is for decay rate. So the decay rate of the dark matter particle and then the Bond's annihilation cross section. So even if you don't find dark matter, you can set pretty good limits on what the physical properties of the particle should be. So what's up next is doing this for the rest of the X band. Supposed to get done this week, but it didn't happen. Once we do that, we can expect possible dark matter signal candidates, really anything above 3 sigma in our raw asymmetries to make sure we're not missing dark matter. And then something I want to try is using different halo models and seeing how that impacts the sensitivity of the search, because we don't know for sure how the dark matter in our galaxy is distributed. And hopefully we'll find dark matter. And 20 years from now, I'll come back here with a parking space. That's not my man can dream. Yeah, I'm happy to take any questions.
Thanks. Questions?
Yeah, I have this is probably like a naive question, but how do we know that the dark matter halo is static?
This is pushing kind of the boundaries of my knowledge, but the dark matter, these dark matter halos kind of form very early in the universe before galaxies form, and the galaxies actually kind of fall into the dark matter halos because there's gravitational interaction between the dark matter halo and just normal matter that falls in. So it's not like the same formation process. So, well, it's not like completely static. There's probably a little bit of rotational velocity, but it should be, in most places, it should be virialized and static relative to the ordinary matter, like stars and gas and dust and things.
So if you don't find anything in X band, when you've got some sort of stronger constraints on the dark matter properties, does that inform, maybe this is a question for Carl as well, does that inform sort of any of the lab experiments and sort of what the priorities should be there?
Yeah, so the thing about the search is that it's what we call a model independent search. So we're not going to get as much in terms of sensitivity when you compare it with the most sensitive experiments, which are searching for axions with very weak couplings. So you're not going to like reach the sensitivity of the most sensitive experiment searching for axions, but you are also probing for any dark matter particle in this sort of mass range between 1 and 11 gigahertz. So if we don't find anything, then we can eliminate any kind of dark matter particle in that mass range up to that sensitivity limit. So it's not going to set any like new limits, but at least for like well-known candidates like the axion, but it will kind of eliminate any possibility of dark matter in that sort of region of parameter space. Hope that was
okay. Thank you, Benjamin. Next up is Hoang.
Hi everyone, my name is Ha. I'm a rising senior at the University of Chicago. In the summer, I've been working with Dr. Danny Check, Brian Mackey, and Shnoa Trombley on target selection for study, specifically for condenser surveys on the Meerkat and VLA arrays, in order to identify ways to allocate beams across stars and non-stellar targets so as to maximize scientific return. and Konijn. So currently the Meerkat and the VLA arrays share a single target selector containing about 32 million objects constructed primarily from the catalog, which originally contains about 1.3 billion stars, and the 800 source Exotica catalog, which samples the breadth of astronomical objects from stars to galaxies with a degree of focus on anomalous and extreme objects. The main challenge with this current sample, however, is that the source density gets quite thin towards the galactic poles and at high frequencies where the field of view shrinks. So at some of the current fields of view, we don't actually get any objects, which isn't so efficient in terms of time and resources. In order to improve on this, we are using the Gaia DR3 catalog, which has 500 million more stars than DR2, as well as the new semi-exotic catalog, which is now in fact. Meerkat already uses semi-exotica to an extent, but in somewhat of a naive way. We are also considering the Unwise catalog as a backstop, which adds another 2 billion more potential extragalactic targets, though for this project, we're focusing primarily on the Fulmer 2 catalogs. With this expansion, the next question then is how to decide where to place the coherent beams of each instrument when there are more targets than there are beams in the field. And for study purposes, we identify rarity of the object as a primary focus for this prioritization scheme, as well as striking a balance between stellar and non-stellar targets. I spent the first third or half of the project investigating the density of stars in these catalogs with Gaia DR3 and the semi-exotica catalog. The density towards the poles at the galactic latitude, which is defined as upward of 50 degrees. It's still quite slim, but significantly improved from the previous two catalogs that are used in the current selector. And additionally, with the Unwise catalog, whose objects are extragalactic and thus do not concentrate on the plane of the Milky Way, we expect that the density of at these regions at higher latitudes will see a significant increase. So moving on to the prioritization scheme, we assign each object from the Gaia catalog a proxy rarity score as defined here in the upper left, using a free parameter S0 as the distance of the star and the distance of the star, while each object in the semi-exotica catalog is already assigned a rarity value T, scaled by a free parameter C. We then test 3 ways to allocate the beams for pointing. So strategy 1 uses the scores only and takes the top ranking object regardless of type and where it comes from. Strategy 2 reserves a fraction of the beams first for Gaia stars, and then the remaining fraction goes to the objects by score. And strategy 3 is sort of the opposite of strategy 2, where there's a fraction of the beams are reserved first for the semi-exotica objects. Our results are shown here in these plots on the right, where the y-axis is cumulative star equivalents covered at or below a given a minimum PIRP in log scale. And moving right means you're less sensitive, and only stronger transmitters would be detectable. The y-axis is y-axis is cumulative star equivalence as defined by a non-globular star cluster containing around 1,000 stars. A globular cluster is 1 to the 10 to the 5 stars, and a galaxy or galaxy cluster is upwards of 10 to the 11 stars. Also in log scale, which stacks the contribution from individual stars and integrated stellar mass in galaxies. Large downward steps in these plots are big populations dropping out as sensitivity worsens. So steps at the far left are the very nearest Gaia stars, the broad shelf from 10 to the 14th to 10 to the 18th. Generally speaking, the dashed line here is the incoherent sum method where we're not coherently beamforming. For I guess like our recommendations for common and bright objects, then any strategy should be able to pick them up, but this has already probably been rolled out by previous surveys. If ETI signals are rare and dim, then I guess that's just tough luck for us. If they're rare and bright, incoherent actually does pretty well. If we want to outweigh that, then we need to pretty heavily favor semi-exotic objects. And for common and dim signals, we could possibly prioritize near stars and use strategy 2, which reserves sky stars with small to moderate reserve, or strategy 1 with strong distance and parallax weighting. There's some real world considerations to be further considered in this prioritization scheme, but in order to extend the project as well, there can be applications in other commensal observing facilities based on the configuration, and also a possible extension to optical spectroscopy surveys that use fibers and also need to locate like certain endpoints on a search field. Yeah, thank you for to all my mentors and also all the real adults in the room for doing this, and to the cohort for a really fun summer.
Great, thanks. Questions?
I just want people to know I ate that whole burrito.
One hot.
Same day.
Do you think we could eat a wild burrito though? Like,
Yeah.
Maybe with some help. I think that's a team effort.
Okay, let's move on. And Andres is up next.
Is this show go ahead? Hi everyone, my name is Andres. I'm a rising third year at Yale. I worked this summer with Steve and Caleb Painter on a project on RFI statistics at the Green Bank Telescope. So the elevator pitch is most of the radio society is throwing out RFI, which is just man-made signals that we don't care about because it's not aliens. And the idea of this project is to just gather statistics about how this RFI shows up at Green Bank, which is a massive radio telescope in West Virginia, so we can get better at throwing it out. So for the beginning of the summer, I started with Pickles, which is a pipeline you've heard before. And this morning, I used askertosis to try to do a ETI, like a technosignature search on Green Bank data. Part of the outputs from this pipeline were there was a big table of several million level 0 blocks, which are just snippets of GBT outputs that pass a loose is there a signal here check. However, this pipeline was very much made for a technosignature search, while my project is more focused on RFI. So we figured it would be smart to try to make my own pipeline that is specifically made for finding RFI. So I present BART, the breakthrough analysis of RFI trends. It's just a relatively simple pipeline for finding RFI and Green Bank data. I built it in with all these bells and whistles. It's got a Python API. You can call it programmatically. You can also call it from the command line. It does some parallelization stuff to go through multiple files at the same time. It's got this. It's got some structure for monitoring like how long is left in your run and if stuff is going right or not. And I even made this run manager like feature that the problem of I have to go through a list of files and do some processing on them is a really common one in this field. So you can just focus on the processing and just import this thing and it worries about the parallelizing stuff, the progress stuff, and so forth. So anyway, the way it works is you just look at the middle time slice and it throws some filters on the energy values, and if it passes them, then there's probably a signal here, and it works surprisingly well. It also tacks on some extra things like whether it's a blip or not and how wide the signal is. You can ask me about it. Anyway, I ran this code on about 60,000 files and got a big table of 88 million hits. And yeah, I'm just gonna show you some ways I sliced up those hits. But anyway, one way we sliced them up is I made histograms of the hit distribution as a function of azimuth. And then you do the same thing with the sample in general, and then you divide these two, you normalize the hits by the number of files in that direction, and you get this hit rate versus azimuth plot, which tells you look in this direction, how many hits you expect to see. And if you grab that plot and you curl it around in a circle and you slap it on top of a screenshot of Google Maps where the GBT is, then you can get a big idea of where the RFI is coming from. Now, unfortunately, this section of the this sample of the hits doesn't have any strong trends. You get something a little bit more, a little stronger when you look at UN2 Wi-Fi. But if you look at the actual observations on an azimuth altitude plot, you see that there's just some bright files in that direction. Nothing really systematic. We also try to see if we would see more hits in the upper X band as the amount of satellites, as the amount of Starlink satellites increased, and we didn't. And yeah, so if you make one of those radar plots for the full range, you actually see a really strong southward bias. If you cut it down to just the upper X band, it's even stronger. And this is one of the nicer results we've seen, is that a lot of the hits we get are from the geosync belt. This plot is essentially this radar one, but you encode altitude into the radial direction, and now you have like a radial 2D histogram. And as you can see, most of the hits are towards the south, where you expect the geosync band of satellites to show up on GreenMake data. Now, if you animate this plot with a scrolling window to see to limit which hits you're actually looking at, then you get this nice animation of the gigabit babies. But yeah, as you can see, you get like very loud blurs at around 4 gigahertz and 11 gigahertz, which is where these geosync satellites need to communicate really quickly. Some of these plots. This is the same thing, but normalized, like I normalized the radar plot. See more of the same thing. Yeah, and then some other ways that we didn't quite see anything is that as you go on through the years, you kind of just keep that lower southward bias, but aside from that, it's just kind of noise. We didn't see any trends by day of week or hour of day, and nothing statistically significant anyway. And this is what that plot looks like with the animated graphs. That's just kind of noisy. Anyway, I'd like to thank my mentors and the Breakthrough Listen program for funding my summer here, and I'd like to take any questions.
Thanks. Questions? And if there's questions online, feel free to unmute.
Question. Go ahead. Maybe I'll say you that question. Oh, okay. This is super interesting. How easy would it be to port this to other instruments like the ATA?
So the architecture around it is pretty telescope agnostic. The specific pipeline I made, I mean, if it's just waterfall files, you just have to change some header stuff. I tried it on Parks data. It doesn't crash, but I did test it. That could be a thing for maybe future intern to figure out. But aside from that, it's relatively telescope agnostic. I don't think it should be too difficult to port over.
Any questions?
Your pipeline name?
So I called it BART. Well, mostly because Steve suggested it.
Where's your slide?
But I really like the name because I did a lot of BART this summer. Living in Dublin, California with my aunt and uncle, to commute about an hour each way, which is fine. I saved a lot of money. Anyway, if you throw the amount of BARTing I did with the speed of BART into ChatGPT, it'll make a special relativity calculation of how much younger I am than if I didn't do BART. I'm about 270 picoseconds younger than the version of me that just lived in Berkeley.
You put the part that says like biologically insignificant.
I did.
All right. On that note, let's move on. Our next speaker is Valeria.
Hi everyone, my name is Valeria Garcia Lopez and Bryson Junior at Cornell University. I'm gonna talk to you about the project that I have been working for the last 10 weeks with Sophia and James. The name is using the idea to follow up transients alert from the LSST. So the project overview was the creation of an alert filter for the region of the sky that can be seen by the ZTF and the ATA, and then later on with the LSST, kind of like identifying some targets that will be worth to look at, and maybe performing some observations with the ATA, and hopefully analyze those observations and create a pipeline of how to find radio technosignatures. But the question here is kind of like, how do you know what to look for? That's a really good question, and it was kind of like hard at the beginning. So I spent the first couple of weeks kind of like learning about brokers. In this case, I used last year that used the information for the ZTF telescope, and I created some watch list filters and watch maps, also with the help of Professor Rafaela and her team that they are experts on transients. I kind of created a table so I can see all the subtypes and types of events that it can be observed by the ZTF telescope, and kind of like doing some research literature if they have already some like radio information or radio detection at some point. And I classify them as 3 groups, like the things that are worth to follow, the ones that are kind of like plan B, and the ones that you want to avoid. But miracles happened, and the universe decided to send us the 3i Atlas. Everybody got excited on July 1st, 2025. A new interstellar object was kind of like entering into our galaxy. So why not to observe it? You know, it's there. And it was a really good idea. So Sophia started with the plan of making some observations with the ATA from 1 to 9 gigahertz. And this was really good because why is the 3i Atlas so famous? Okay, the first one is an interstellar object. It's moving fast. It just entered to our galaxy, and it's doing a hyperbolic trajectory that is pretty similar to the one that we saw with the Oumuamua. So we did some observation from 1 to 9 gigahertz. We divided it into chunks because that's a lot. Into low, mid, and high frequency, we did like 5 nights of observations with 5 minutes performance cuts. And after the 5th night, we got 7.6 hours of data. That is around 75 million hits or data points. That it's a lot and it's good, but also we needed to clean it. So for cleaning methods, we decided to go for blanking ranges and the drift rate. For blanking ranges, it was kind of like manually, and that was kind of like my main work during this project, that it was kind of like going through the images and look at the ones with like large clusters of hits and get rid of those. And for the drift rate, we needed to find the radial acceleration that we got about 3.2 and to 3.5 times 10 to the negative 5 kilometers per square second, which was pretty good. So with that information, we were able to create this kind of like plot that is really nice. And the yellow shadows are the kind of like periods of time that we were observing at the target at that point. So we got the mean and the standard deviation of the acceleration, and we're able to get the drift rate of a signal that will come from the 3i Atlas. This plot in the middle is kind of like the blanking ranges, kind of like the data around the frequencies that we were using, so low, mid, and high. The red bars, you can see it's kind of like all the hits, and it's going down after the filtering, the blanking ranges with the blue one and the red one and the green one. You can barely see it. It's kind of like the last filter. So from 75 million went all the way down to 2 million, which it was really nice. This is another kind of like perspective. This is instead of frequencies, the drift rate, and we can see here the limits. So the real question, did we find technological advanced life on the Triad Atlas? No. But we got 211 events that were to follow, that we found that it was like just radio frequency interference. We can have an example here that we found kind of like a signal here, but we ended up concluding that it was from the Irradium satellite that is kind of like being phone communications, and we don't see any like radio acceleration or something like that. So yeah, it was just kind of noise. But even though we didn't detect any convincing technosignatures, it still is important to know what sensitivity our research was and what kind of like transmitter we could have detected. So we calculated the 16 equivalent flux density and the minimum detectable narrow flux density as well. And with that, the equivalent isotropic 3D power. That were kind of like decent numbers, and this is helpful because it quantifies our observations and it lets like for future researchers to see whether their results will be more sensitivity or longer observations to improve their limits. Just for like to wrap up, the last week we kind of worked on visualization. Like we wonder what will a radio signature coming from the Triad Atlas look like. And this is kind of like a narrow band that we kind of created, and we can see the drift rates in here. We put those boundaries. And this is kind of cool because it helps as a base for other research to see like, oh, okay, this is gonna be how it looks like. A narrow band from the Triad Atlas if they want to do more research in the future. And also it gives hope that if you still, I don't know, do research in interstellar objects, at some point you're gonna find something because there's a big possibility for that. So these are some of the takeaways, and I just want to say thank you to everyone for the opportunity. I'm so glad I was able to be part of this project.
Great, thanks. Time for one quick question. There is one. All right, let's move on. Jessica is up next.
Okay. Hello, I'm Jessica. I'm a rising senior at Penn studying computer science, and this summer I work with Steve and Ben Jacobson-Bell on multi-scale classification of Green Bank telescope signals. So data is stored in 3 different resolutions, and there's different trade-offs between time and frequency, and previous work usually uses the high spectral resolution data. However, satellite RFI can span kilohertz or even megahertz, so using only fine res files can make us fixate on substructure while missing its broader pattern. And this is an example of how the same RFI can look different at different scales. So this motivates us to incorporate mid-res files to help us better reject RFI in high-res files. For this work, I focus mainly on L-band from 500 megahertz to 650 megahertz because that's a very RFI-heavy region, but it can be generalized. Previous work, Carmen Choza conducted a turbo study survey of 97 galaxies and returned around 6 million false positives. And then Ben applied clustering methods to filter those hits and reduce the haystack. And in this work, we developed a multi-scale classification of the same signals using more machine learning techniques. So turbo study works pretty well with high-res files, but those thresholds may miss signals in mid-res files. So it may not translate over well because those narrow signals get smeared. So in this work, we use an unsupervised edge detection method. We combine 4 different methods and just use like a mixture of experts type of architecture. We also only keep coarse channels that have a kurtosis value of at least 7 because if they're any lower, like they're most likely noise. And this is an example of some of the bounding boxes that we make using this unsupervised framework. And then incorporating high-res files, we use the turbo study hits from Carmen Choza, and we input those into a vision transformer to encode them into a 32-dimensional latent space. We can visualize those latent spaces with this t-SNE plot. It's colored by signal frequency, but we don't actually incorporate it in the latent space in any way. And then we can eliminate these some of these signals based on the number of signals in mid-res that have an overlap in frequency, and we can also adjust this threshold for the number of signals that need to overlap. So we took a subset of around 38,000 signals from Carmen's outputs. And then this is what happens if we say like, I think later in our pipeline, we mainly use this output. So we say like, if a signal overlaps with at least 10 bounding boxes that we found in high res, then we should throw it out because it's most likely RFI. And then that lets us get rid of around 26,000 signals. We can also perform some clustering analysis. So this is one cluster with signals that are mainly around 1620 to 1625 megahertz, so like most likely iridium. And then we can kind of see like the 10 signals with the lowest similarity scores and then 10 signals with the highest similarity scores. And we can see that like they're, except for maybe this one, they're pretty morphologically similar. So we can understand why they're in the same cluster, although these look a little bit different, which explains the lower similarity score. And this trend also applies in other clusters. So this is a cluster with signals around 1530, 1540 megahertz-ish. And again, this is a cluster with signals around 1570, 1575 megahertz. You can see they're pretty similar, but like still a little bit different. So the clustering matches up the way that we expect. So we should kind of incorporate clustering into our analysis of which signals to keep or exclude, because the idea is that if a signal is like potentially an outlier, maybe it's an anomalous signal, we should keep it for further analysis later down the line. So we can use a Gaussian kernel density estimator to estimate those point densities in the 32-dimension latent space. We can, for this work, we flag points in the lowest 5% of densities as potential anomalies that we should keep. This threshold can also be adjusted as needed, depending on how conservative you want to be. With this threshold, we remove around 36,000 signals, and then we can combine the two conditions. So we only keep signals that appear in less than 10 mid-res bounding boxes and are also flagged as low density. And this lets us get rid of around 25K signals. So yeah, conclusion, we use unsupervised edge detection to incorporate mid-res signals for improved fine-res signal analysis. Future work, we can think about maybe incorporating some domain features in the latent space, exploring other clustering and anomaly metrics, and expanding to more diverse data sets and signals. Those are my references, and thank you, that's all. Thank you.
Questions?
I'm so speedy.
Yeah.
I think you mentioned the latent space was 32-dimensional.
Yes.
I don't know if this is kind of like other methods where those dimensions don't necessarily map to physical parameters, but if they do, are there like examples like, oh, it's by one of the dimensions is frequency and another one is drift, or is it like linear combinations of those things?
So I think like people use different ways of like extracting latent spaces. So like I know Peter Ma, he used a very small encoder and then like using the latent space, then used like 13 like features and use that to cluster. I take the high res, those hits from Carmen, and then I stick them into a vision transformer. It's pre-trained, so I don't do any like additional like training on it. It like compresses it to I think it's like 224 by 224, and then it does the encoding, and then it actually outputs to like a 768 dimension like vector, and then we do PCA down to 32. So that's how the 32 dimension comes about. I don't know if that answers your question.
So it's not like each of those dimensions maps to
Like
something that
no.
Blips or turbos that you found.
No, yeah, but we said, but like maybe we can discuss like, we've discussed like incorporating frequency, but we also don't want it to memorize what signals appear on which frequency, so yeah.
Any other questions? Again, folks online, feel free to unmute if you have questions. Okay, let's move on, and next up is Maddie.
Hey everyone, my name is Maddie. My project title is what's actually out there, an empirical and statistical hybrid catalog approach to steady survey volume. So basically combining the observational and statistical approaches to better refine transmit rate and continuous waveform metrics. I'm from New York. I go to Queens College studying physics education. My mentor supervisor is Macy. And yeah. Okay, so in terms of a background for my project, so in the past, study surveys have targeted single stars, single pointings, but starting with the WGNS approach, they actually consider much broader coverage, considering the full width half maximum and using the Gaia catalog. The full width half maximum of the telescope's beam is the angular span over which a source's brightness falls to half its peak. And this dramatically increases the number of targets and significantly tightens the upper limits of transmitter rates, giving much stricter limits. Then this approach was extended to the extragalactic realm with the Gary and Simeon paper, using another observational catalog called NED to account for distance systems. And then there are statistical models to incorporate as well, such as SynthPop for Milky Way analysis. And paper, and we use the galaxy stellar mass function to fill in gaps where empirical catalogs are incomplete. And for my project, we directly build on these foundations, combining the empirical catalogs and population modeling using software, yielding more robust and stringent constraints. In terms of the methodology, we developed something called Beam SETI, which is our pipeline, which stands for Background Extragalactic and Milky Way SETI. Thanks to Steve for coming up with that. The process starts with a standardized table of survey fields, branches into the 4 complementary approaches, Gaia, SynthPop, NED, and UNO, and simulates full Milky Way and stellar population. On the extragalactic side, we have NED for real galaxies using adaptive clustering and distances from NED redshift independent distances. And then from this, we calculate EIRP, transmitter rate, sensitivity metrics, and error calculations. And then these feed into comparative analyses and visualizations. These results are compiled from the 834 fields, from the GPT-L receiver, from the Price et al. Catalog, which was fully, I think, about 1711 fields. The first figure shows a direct comparison between transmitter rate and ERP on the log scale for 4 different survey approaches. Gaia's transmitter rate drops off much slower than SynthPop because it accounts for a lot less stars at a much closer distance, so it undercounts faint and distant stars, leaving gaps beyond about 10 kiloparsecs. SynthPop adds over 1 million stars and much larger distances, yielding a much steeper slope and setting much tighter limits on the prevalence of detectable transmitters in the Milky Way. And then for comparing on the extragalactic realm, we have NED and the UNO approach. The NED approach extends coverage to galaxies, assuming each galaxy has about 10 to the 11 stars, while the UNO uses the galaxy stellar mass function, which is, even though more conservative than 10 to the 11 stars, it delivers a much stricter transmitter rate constraint due to it encompassing a much broader model and returning just a lot more stars because NED is pretty incomplete in terms of distances. And then on the CMDs, they make clear that the observational catalogs like SynthPop incorporate a lot of stars that Gaia can miss. They're bluer and they're fainter and extend to farther distances. In terms of the extragalactic realm, NED returns a lot of sources, but only 1% of them have reliable redshift measurements from which we can extract ERP and transmitter rate. And UNO stars at a much tighter transmitter rate, so it restricts it sets a much tighter limit, and so the observational catalogs again restrict our ability to accurately measure, say, survey sensitivity. Yeah. In terms of what we've gained from this, a hybrid approach is essential because empirical catalogs like Gaia and NIT provide reliable detections of stars and galaxies. They're real, but they miss many objects and recover only faint and bright and close by stars and galaxies. And so the hybrid approach gives a better picture of the full SETI survey volume. And we should consider hybrid approaches in the future, combining observational model data to provide the most robust survey sensitivity metrics for SETI. Looking forward, we want to address further differences between the empirical and statistical approaches. They are quite different. Maybe we could try to understand that a little bit better, the assumptions, etc., by comparing across fields, bands, approaches, and cross-validate, reconcile these differences, incorporate time domain effects, refine stellar population assumptions like 10 to the 11 stars per galaxy, and apply this to future fields to guide future observational strategies. Yeah, so thank you everyone, and thanks to Macy and the team. An amazing summer. Yeah.
Great. Thanks. Time for a quick question. Anyone online? Okay, there are no questions, then we will move on to Emma.
Hi everyone, I'm Emma. I'm a student here at UC Berkeley, and this summer I worked with my mentor Jim on searching for lasers within 100 parsecs using high-resolution spectroscopy. So our goals here were to find high-resolution spectra belonging to stars in the Gaia catalog of nearby stars, and these are all stars within 100 parsecs, and then to search these spectra for narrowband lasers. This plot at the bottom left is an example of what we were kind of hoping to find. That little red peak in the center is one I artificially injected, but these are the kind of technosignatures we're looking for. The plot on the right was made by Jim, and it's just showing the coverage of stars in the GCNS that we have high resolution spectra for, although he looked at a few catalogs that I did not use in my experiment. So I looked at 9 catalogs total and tried to cross-match them with GCNS, and this is the coverage that they span on an HR diagram. The bottom right is a plot of the full GCNS, and out of these 9 catalogs, I started looking at spectra from GALA, and that is because it has over 4,000 stars within 100 parsecs. There's a lot of main sequence stars. It was also one of the most accessible. And it has a high resolution of R equal to 28,000. It also has 4 camera bands, which is nice, and this plot on the bottom shows that. In terms of injections, this was to test our detection sensitivity, and so we did this by injecting a narrow Gaussian peak, full with half maximum of 0.1 angstroms. And this box on the bottom is a zoomed in version of that. The blue is just an original spectrum from GALA, and then I just injected the red Gaussian there. And then for the recovery process, I took SciPy's built-in find peaks function, and I just modify it to look for widths less than 13 angstroms or 2 pixels on the scales that the spectra were from. And I also had to teach it to measure height from the normalized continuum because we were using normalized spectra, and so this was at flux equal to 1. And we were trying to look for especially like tall signals so that we wouldn't get confused with noise. So we were searching for peaks taller than 20% of the maximum emission. And then so we repeated this injection and recovery process 1,000 times independently per spectrum, and we used a randomized wavelength and injection amplitude each time. This spectrum is an example of a failed detection because that dotted black line is where we actually injected the laser. But as you can see, there's a lot of like atmospheric noise in this range of wavelength. So there's all these other peaks that we detected, but none of them are what we injected. And after performing this on 10 objects out of the 4,000 in GALA. So this is 40 spectra because there's 4 cameras for each object. I was able to obtain this completeness curve showing how well we can recover for each amplitude of laser we inject. And this is showing how our recovery is dependent on amplitude and wavelength. These 4 columns are the 4 cameras in GALA. And so it actually does pretty well for amplitudes above 20 flux units. And doing some more careful statistics, we found that the minimal detectable amplitude to 68% was about 30% of the max flux, and this corresponds to a laser luminosity at the source of 1 kilowatt. And this calculation was done from a former intern at SETI, Anna Zuckerman's paper. The equation is below. And what was interesting is we found this false positive rate, which is basically how many peaks we detect that weren't injected by us, to be about 1.5 per spectrum. In the future, I'm hoping to do more characterization on that. And yeah, all this data was just from a sample of 10 stars out of the over 4,000 total. And yeah, just wrapping up, I just wanted to thank Jim, Steve, and all the mentors on SETI for your guidance, and also my fellow interns for all your support and teaching me how to play hack and sacks. And yeah, I'm gonna leave it on this slide, and I'm happy to answer any questions.
Thanks. Questions?
Do any of the metrics on this slide vary over the 4 different bands, 4 different configurations we have on these?
Yeah, that's a good question. I actually haven't isolated it by camera exactly. The most analysis I've done was from this plot. But you can kind of see, especially with the longer wavelengths, the I band, because that's where all the atmospheric noise is, it's kind of performing worse. So I'm going to do more characterization on that too.
I'm curious, so this 1 kilowatt laser, that's the intrinsic power of the laser, and then that's hooked up to some aperture of a telescope, I guess, as well?
Yeah, so we are making a lot of assumptions with this calculation because we are basically assuming the aperture of the laser emission is the same as the aperture of the telescope we're detecting it with. Also, I hope to do more robust noise calculations with my data in the future because we've made some assumptions about what the noise is in that data, but yeah, those are those.
But on the other end, I mean, presumably you have some mirror basically that you're firing the laser at to
yeah. So
collimate that, or you're just launching a laser straight out and then picking it up with the mirror at this end.
Yeah, so yeah, it'd be like a laser picked up by the GALA instrument, like that mirror size.
So just the mirror on this end and the laser on the other.
Yeah, just the mirror.
Any other questions? Okay, if not, then we will move on to Ella.
Okay, so hi, my name is Ella Bishop. I am from the University of Virginia, a rising 3rd year, and this is my project, which I had the help of ChatGPT naming Radar. It's the RFI aware detection of anomalous radio technosignatures. And my supervisors for this summer were Shanoa Tremblay, Daniel Check, and David McMahon. So to get started, do a little bit of background. The project initially for me was just going to be working with the VLA, but we ended up incorporating both VLA and Meerkat data. So a little bit of background on those. The VLA is an array of 27 antenna located in New Mexico. Specifically, we were using the cosmic backend that allowed us to commensally collect data for SETI searches. The data that was collected ranged anywhere from L to K U-band, but we didn't use all of those bands due to RFI restrictions. Also, there were 2 different kinds of survey methods for the VLA. There was V-LoLSS, which is kind of a sky survey, and then source pointing method. So the telescope pointed at Gaia sources. And there was also coherent and incoherent beamforming that was used with the VLA data. And then for Meerkat, just an array of 64 antenna located in South Africa. The data ranges from the UHF band to the L band. It was calibrated with BLUs rather than SETI core. And the source pointing methods was the main way that the hits were created. So that was with the Gaia and Exotica catalogs. So the motivation behind this, for more for my like aspect of the project, because Jay will continue on with, we work together. But Cosmic is the backend that produces like a multitude of hits. And in order to go through that like effectively, we need to filter out a lot of RFI and unreasonable candidates to actually hone in on the anomalous ones. And so previous pipelines have been made, such as the Artistic and Crickets pipelines that kind of reduce this RFI. Artistic is more similar to my approach with the anomalous or the algorithmic approach, whereas Crickets is it's a kurtosis evaluation. But basically, the goal was to create a pipeline that took in large and varying data sets from your CAD and VLA, preprocessed them, and filtered out RFI hits to narrow down the candidate and all the signals. So this is kind of the structure of the pipeline that I was able to create. It starts off with feeding in the different data sets and reformats them so that it can be pre-processed and then input into the core pipeline. The starting point of this is definitely like the coherent versus incoherent hits if there are pairs, because then we can do power ratio calculations, which is a pretty strong threshold for like flagging actual RFI. So we see that once you calculate the power thresholds and you figure out the configurations, you can then do a cross beam analysis. So for VLA, there was usually anywhere from 1 to 6 beams, the 6th beam being the incoherent. So after splitting up the coherent and incoherent hits, I basically was now analyzing if hits were found within 1 to 2 beams, 3 to 5 beams for VLA, or 6 or more for Meerkat, with upper thresholds of 6 beams for VLA being RFI or just the incoherent or be overlapping too many times for it to be a signal, and for greater than 50 beams for Meerkat. And then the core process or part of this pipeline was the flagging process. And so some of the conditionals here are the sources spatially separated between beams. So are they within the same kind of observation? Are they like wide ends of these beams or different, very spatially separated, so more likely RFI than close together where we would expect a source to come from? Are the hits with same frequency and drift rate found at the same time, found across time at the same place? Are hits with the same frequency and drift rate found across multiple fields of view? And then the power ratios, which is a really good thing, or really honed in on those hits for VLA. Was it within 3 to 5, which is, I'll explain a bit more, but that's basically the power ratio should be proportional to the square root of the number of antenna. And there's anywhere from, like I said, 0 to 27. And then the SNR is if it's less than 50. So all of those conditionals, they would basically produce a flag, and the values below, if there are 0 flags, we would consider that completely clean. 1 flag is maybe RFI, and greater than 1 is definitely RFI. So these are just some preliminary results right now. So those are the hits that have been flagged once, so possibly seen multiple times in a same place, for example. And we can see the percentages of the clean, how much data has been cleaned was, we're pretty high with the conditionals that we have. So that was really nice to see, not 998%, whoops, that is a typo, 98.9%. My bad. But yeah, these are preliminary results, and more specifically, these are just kind of what we're seeing with each flagging step. So I want to just note that the condition 2 is the power ratio. So yeah, but a lot of it is just this global where we see the same hit across time in the same place. And across multiple beams. But yeah, so next steps, wrap up any last RFI flagging methods for Meerkat, publish the pipeline to GitHub, write up methods, use an overleaf, and kind of get the last stamp files to correlate more with what Jay's doing, and maybe find some aliens. But I want to do special thank you. Gosh, this is lagging. To Mr. James. Zach, Hat Creek Bowling Alley, 2 Messed Up Ankles, the Exploratorium Weighted Blankets, and of course my mentors. So I'll take questions now.
Mr. Buffas really took one for the team.
Yeah.
Thanks. Questions?
That is you.
Me, no, yeah, that's me in front of the shiz. Yes, you, yeah.
This is super cool and also a very challenging problem to work on, I know. Something that we do at ATA is if we don't have a power ratio, like if we don't have a matched hit, we go in and take little snippets of the data and like do a couple of metrics to try to compare the brightness of the signal of both.
Okay.
I don't know if that's something you thought about or just for this many signals, that's completely impractical.
No, I think that is actually something, we go back to the artistic pipeline. I think there is something in here, I guess you can't really see it, but I think there was something with a brightness, like intensity threshold that was used as well in consideration. So yeah, that would be great, because I think that's more, with the VLA, we have a good amount of metrics, like we've gotten the data hits down from like, I don't know, like 6 million to like a few hundred with just getting rid of the RFI and the power ratios. But with Meerkat, I think it'll definitely be significant to have that. So I'll probably take that into account with them.
Any other questions? All right, we will move on to our last talk in this session, and that's from Jay.
Okay, so my name is Jay Montgomery, and I'm working under Chenoa, Daniel, and David, or Chenoa, Tremblay, Daniel Check, and David McMahon, and I'm also working with Ella. So, okay, so Ella already introduced the VLA and Meerkat. They're right here. They generate lots of hits and stamps files. So we're both creating pipelines to go through those hits and stamps and find interesting signals. The difference between ours, so mine is clues, hers is radar. I don't think I explained it, sorry. Clues stands for Cosmic/BLU's Unsupervised Exploration for Signals. So the differences between ours are, hers is algorithmic. So she's making decisions about what should an extraterrestrial intelligence signal look like, and then excluding based on that. I am not making any decisions. I'm just like, okay, here you go. Here's the data, look for weird stuff. And it's looking for weird stuff in the stamp files, which makes it actually a lot slower because it has to load in a lot more data. It has to load in like a full-on frequency and time snippet around the actual hit, whereas Ella's is much faster because it just uses hits files, which are the outputs, where it's just like statistics about the signal. And then mine has a form of ranking because all of the inputs you put in, it'll just rank from most to least anomalous. Ella's has limited ranking. There's a bunch of other differences, but these are some of the main ones. And the reason it helps that we're both doing pipelines is we can actually compare these two methods once we're working. So like we're working on the same data, and we're able to compare these two methods. We haven't fully been able to yet because we were still waiting for data from Cosmic, the stamp files. I don't know if they're here yet, but we were just working on limited Meerkat data. We do have the hits files from Cosmic though, but I'm working with these. These are the stamp files, so you can see it's a snippet around the actual hit. Cosmic stamp files are 16 time steps. Meerkat stamp files are 290. So I'm resampling the Meerkat to 16 time steps before actually putting it into my pipeline. So this is what the stamp file actually looks like. You have the hit, but then you also have what all of the other antennas were seeing at the time of the hit. This one likely localized RFI because it only appeared in 2 of the antennas. This one likely extraterrestrial because it appeared in all of the antennas. So this is important context for the model to have, or for my pipeline to have. So I stack all of these up together. These are actually much wider than they are tall, so it makes a decent image. And you can see this is all stacked up, and then it gets put into a vision transformer, and then k nearest neighbors distance metric is used. So the vision transformer is pre-trained on a large data set. This is helpful because I was using an autoencoder at first, and training the autoencoder on all the data took a really long time, even though I only had like 300 stamp files. so it wouldn't scale very well. So using a pre-trained vision transformer means that you can still extract a lot of interesting information from the big image without taking a lot of time. So it splits the images into 16 by 16 patches. The reason it's 16 is because each of the antennas has a 16 height. So doing this reduces the amount of weird stuff you would get from patching like over multiple antennas. And then it encodes each of those patches and builds a memory of normal patches. And then to get the anomaly score for each image, you split it into patches, encode those patches, and then compare those patches and the k nearest patches in the memory using a distance metric. And then you get an anomaly score for that stamp based on the top % of the interesting patches. This is similar to the patch core architecture from Roth et al. 2022. They developed that during like an AWS internship or something. So this is what it does. Say this is the input. It creates a heat map of where it detected interesting anomalous patches. So here it detected a bunch like right in the center. You can see that's where most of the interesting stuff is, because these signals are straight down and mainly in the center. So some of the issues of this are currently the memory is being built with just normal looking patches. Like I'm actually using a statistical exclusion to exclude like very, very obvious RFI from the memory, but that's not that good of an idea because it makes common RFI look anomalous. And I want to generate a memory that'll get common RFI in it as well. And I haven't had the chance to generate metrics of how well the pipeline is performing. I've just seen like results of most of the time, the very anomalous ones are signals in all of the antennas, which makes sense. But I want to test that. And then future work, I have to test how the time and memory will scale with larger amounts of data, because currently, again, only like 300 stamps. And also I want to compare the results with what Ella's been working on once the cosmic data is available. Here are my sources, and thank you to my mentors and
Great, thanks. Questions? Yeah, Dave.
I had a question about the heat maps that you showed with the interesting bits. Like some of these have like interesting things all the way across them.
Yeah.
How can that be?
Sometimes depending on what's in the memory, like even noise can get picked up as like very interesting. It's just dependent on like, I don't know, for maybe antenna 0, there was just more noise that we can't really see because the signal is so much stronger. But that's like it picked it up.
What is the next step with those heat maps? So like you could have gotten something similar just by taking the thresholding function for bright pixels across these spectrograms. What did the heat map tell you that doesn't tell you?
I'm not fully sure if I understand what the alternative would be. The thing I'm doing here is like using the vision transformer can probably detect pixels or detect patterns that don't appear as just like super bright, because it can extract like more features from the actual image, and then comparing those to what's in the memory, like you just find anomalies.
Thanks.
Any more questions? Okay, if not, then just wanted to close by thanking everybody. Thanks, folks, for calling in the audience. Thank you very much to our interns for some great work this summer and great presentations. And thank you also to the mentors for all of your hard work, and also additionally to our sponsors from the National Science Foundation and the Breakthrough Initiatives. And we have the Breakthrough Initiatives, the Breakthrough Listen Principal Investigator, Dr. Andrew Simeon, who's online, if you'd like to say a few words in closing, Andrew.
Thanks, Steve. Well, it's nice to meet all of you virtually. I'm sorry that
I didn't get a chance to meet more of you in person, but I've really enjoyed hearing about all your work, and of course, I've been following it via your mentors for the summer. I hope that all of you had a wonderful time working with us, regardless of where your future takes you. I hope you look back on your time with us fondly. And as far as I'm concerned, there's no more profound question we can ask as scientists or engineers or as human beings than what is the nature of intelligence in the universe. And you all had a chance not only to explore that for yourselves, but also to contribute very meaningfully to the progression of the field. Many of your mentors and myself included began our journey in SETI, our careers in SETI, in exactly the same position you guys are all in now as summer research interns. And should you decide that you would like to continue doing research in SETI as you continue your research career, if you go that direction, we certainly would love to have you continue to work with us. As I'm sure you've learned, many of your mentors actually began in an RU program, even in our RU program. So there's a great precedent for that. And I'd also like to echo Steve's thanks to all of the mentors. It's a labor of love, I think, for all of us to work with undergraduate students. We really enjoy it. But it certainly takes a lot of time and energy from your mentors as well. And I'd like to thank all of them for their work as well. So I hope you all have a wonderful and well-earned break from research for a few days. And best of luck in your futures. Thanks, Steve.
Thanks very much, Andrew, and thanks again, everyone. The video of this session will also be posted online if folks want to review it afterwards. Cheers.